Good afternoon. Today we're going to continue working with polynomials as well as rational functions. And for what we have on page 281, okay, we're going back to forming polynomials from given zeros and multiplicities. And for what we have on page 281, okay, now we got in the case of the given zeros. Now for this set, each zero will have a multiplicity value of 1. So the corresponding factors will be just a first degree. Okay, and the overall polynomial is going to be of degree 3. Okay, so we have in setting up our polynomial, and we're going to be looking at arriving at the expanded form. And if we look at the formation of a polynomial that will have these characteristics. Okay, so we have a possible factor that will have a zero value of 1. We can say we have x minus 1. And for negative 6, we can say that x equals negative 6 stems from setting equal to 0 the binomial x plus 6. And for what we have for the zero value of x equals 3, we can say this is going to originate from x minus 3 or any other direct multiple of this. Now, for what we have in the case of the factored form, and we have here, okay, so we got with x minus 1, again corresponding to 1, and then we have the quantity of x plus 6, again just referencing the zero value of negative 6, and again corresponding to the zero value of 3, we have x minus 3. Okay, and so this is a factored form, and if we look at writing an expanded form of this, okay, and what we can do, there's no one way to go about this, but we can multiply the first two binomial expressions together. So we got with x minus 1 and x plus 6. Okay, so if we take the product, we have x times x is x squared, and the outside product we have at 6x, inside product we have at negative x. And if I go ahead and combine the outside and the inside products, okay, we're going to be on the plus side at 5x. And the last product, okay, we have at negative 6. And we have in continuation, now we have x minus 3 that is waiting to be multiplied. Okay. And for what we have in this case, we have attaining the product of a trinomial and a binomial, and there are various ways that you can go about this. And I think what I will do, okay, say if you look at a geometric approach, again this is one approach, and we just have terms in row and column formation. And it really doesn't matter which terms you have for the column headings or which you have for the row headings. Okay, and what I'm going to do here, I'm going to have a 2 by 3 formation, but it could be a 3 by 2. And okay, so we have with the column headings, we'll just let this be x squared and 5x and 6, and for the row headings we have x and minus 3. And looking at filling in the corresponding products, okay, so you have x squared and x, we multiply, we have x cubed, and then we have x squared times negative 3, so we have negative 3x squared. And for the second column we have 5x times x. So this will be at 5x squared. We have 5x times negative 3, so this will be a negative 15x. And for the last column, so we have 6 and x will multiply. We have 6x, and then we have 6 times negative 3, where we have in the last product, here we have a minus 18. Okay, so just taking what we have in the terms. Okay, so we have x cubed is the only third order term. Now let's do a little bit of color coding, and we have combining the square terms in the mix. Now we have negative 3x squared plus 5x squared. So we have at 2x squared, and combining the first order in x terms, we have negative 15x plus 6x. So this will leave us with negative 9x. And we have finally with the last product, again we have at negative 18. Right. And so we have for the overall result, okay, we're going to have, again, a third degree polynomial, and one expanded form is where we have x cubed plus 2x squared minus 9x minus 18. Question?
So is in the first trinomial you had negative 6, and then on the thing over here you have positive 6.
Okay. Now remember, I'm fooling out in advance. Okay, so I got x times x is x squared. I got plus 6x minus x, and then I have negative 1 times 6, which is going to be negative 6.
But then you put in on the trinomial on the top of this little graph that you made.
Gotcha. It was a visual thing. There we go. Make sure you're paying attention. Okay. Alright, so this is what we have. Alright, so we got negative 15x minus 6x. Okay, so this will be a negative 21x. Okay, my bad. Alright, so double checking here. So we got x cubed plus 2x squared. Okay, now we got negative 21x, and we have minus 18. Alright. Alright, now, in the case of another polynomial to form, okay, now we're going to have non-integer that is in the mix. Okay, and now we got for the zeros. Okay, now we got 2 and 5 halves. Now each of these will have a multiplicity of 1. And then we have with the third, okay, we're going to have 0, and only 0 is going to have a multiplicity of 3. And we'll have for the degree of the polynomial, okay, this will be 5th order. Alright, so we have just checking, okay, so we have with 2, okay, we have x minus 2, 5 halves, we can say we have x minus 5 halves, and we can raise the coefficients on this, and for 0 we can say we have x, and since 0 has a multiplicity of 3, okay, we can say we have x to the third. Okay, and okay, so a factored form of what we have here. Okay, now we've got f of x and we have is equal to the quantity of x minus 2. We have times the quantity of x minus 5 halves. And we have times the quantity of, okay, after this you have times x cubed. And what you can do now, you can leave this particular factored form, but you can also take care of the fraction. Okay, and so I can just multiply the second factor by 2. Again, this approach is optional. Okay, so I've got x minus 2 and 2 over x minus 5 halves. Okay, so this will be 2x minus 5. And I have x cubed, which follows. Okay, so if I multiply, okay, so we have with the first product, okay, so you have 2x squared, and you got negative 5x, and then negative 4x, okay, so we have minus 9x, and negative 2 times negative 5, okay, so this will be a positive 10, and we have multiplied by x cubed, and then we have for the follow through. Okay, so if I distribute x cubed over this second order trinomial, okay, we're going to have 2x to the 5th minus 9x to the 4th and we have plus 10x cubed. Now I'll just mention, okay, if I had kept the original formation and multiplied the factors as they were, okay, without even changing x minus 5 halves, you're still going to have the same zeros and multiplicities. Okay, so if I multiply directly, so I would have x squared, and we would have negative 5 halves x, and minus 2x, so you have negative 5 halves x minus 4 halves x, so I have a negative 9 halves of x, and negative 2 times negative 5 halves, okay, that's going to be a positive 5, and we have times x cubed, so another possible expanded form answer, okay, we would have x to the 5th minus 9 halves of x to the 4th plus 5x cubed. Okay, and those coefficients will be exactly half of what I attained moments earlier. Okay, now in the crossover, going back to working with rational functions, and we have on page 316, okay, and looking at domain and vertical asymptotes. Now we're going to cross over to looking at other types of asymptotes, okay, but for what we have right now, okay, for number 7, okay, we have the function f of x is equal to x squared minus 25, okay, and this is going to be all over x minus 5. Okay. Now for what we have in the case of the domain, okay, again, for fractions, okay, we cannot have zero-valued denominators. Okay, so you have x minus 5 cannot be 0. Okay, so we have that x cannot be equal to 5. And so we're going to have for the domain, again, we have at the lower end, okay, we have those values of x which will be less than 5. And for the upper half, we'll have those values of x which will be greater than 5. Now, in the case of whether we're going to have a vertical asymptote, okay, to stem from the excluded value of 5. Okay, so looking at what I have in the ratios, I have the difference of squares over x minus 5. And if I go ahead and write in factored form, okay, so I have the quantity of x plus 5 times that of x minus 5, so we have all over x minus 5. Guess what? We have x minus 5 in common. And for f of x, okay, this ratio simplifies to x plus 5. Alright, And so now in terms of whether we have a vertical asymptote, this is what we have had to happen. Okay, now x minus 5 completely cancels out. And if the factor in the denominator completely cancels out, that means that the corresponding zero, okay, instead of becoming a vertical asymptote, we're going to have it to end up as a hole in the graph. Okay. So in this case, we're not going to have a vertical asymptote, and just providing a visual on this one. And this is what the graph is going to look like. Okay, so for what we have in this case, right? So we have our function f of x, which again we have equal to x squared minus 25 over x minus 5. Now, if you notice, okay, now the ratio does reduce to x plus 5, and had the function been given as f of x or y is equal to x plus 5, I would have a line that is running continuously. But because of the original formation with the ratio as opposed to x plus 5 from the start, again, I had that restriction that the denominator cannot be 0. So 5 is excluded and cannot be part of the graph. And with the factor canceling out, we end up with a hole in the graph. Okay. And it's because of that restriction and with x minus 5 canceling. All right. And for what we have in the case of number 8, okay, now we got a function g of x. And it looks like we have a difference, so squares, yeah. So I have x squared minus 9. And that is going to be all over x minus 3. Okay. And partial history repeating, we have one denominator expression. And again, for the function to be defined, okay, it cannot be 0. And in the case of x minus 3, okay, we have that x cannot be equal to 3. And with the domain, okay, we have one exclusion, and the lower portion will be those values x less than 3, and the upper half, okay, we have those values which are greater than 3. Looking at putting x squared minus 9 over x minus 3 in simplest terms. Okay, so we have with x squared minus 9, okay, we have factoring out to x plus 3 and x minus 3. And we have all over x minus 3. So you have different binomial, okay, but you have the denominator to completely cancel. Okay, so again, x minus 3 is going to cancel out. And for the value of 3, because of the complete cancellation, okay, x equals 3 is going to be a whole. And for g of x, okay, so after the reduction, okay, so g of x is going to come out to x plus 3. And most of the graph of g of x, okay, almost all of it is going to be along the lines of y is equal to x plus 3. but where you're going to have the value of x equals 3 to be excluded. Yes.
I'm sorry, I don't mean to keep interrupting you. So for this one and the last one, are you saying there's no vertical asymptote? So like
No vertical.
like -5 wouldn't be the answer for 7, and -3
if
wouldn't be 8.
There's no vertical asymptote whatsoever. So in other words, it's like there's going to be a destination. If the domain has any exclusions, there's a destination for the exclusion. It's either going to become a hole in the graph, or it's going to become a vertical asymptote. And had, let's say in the first graph, if x minus 5 had not canceled, instead of a hole, you would have had a vertical line that would split the graph of f of x. And the same thing with x equals 3. Had the factor x minus 3 remains in the denominator after simplified form, instead of this hole that appears, you would have a vertical boundary that would show up. It's kind of binary. Okay, if you have any exclusions in the domain, it's either going to be a hole or it's just going to be a vertical asymptote.
Okay, thanks.
And now, we're going to have a situation with asymptotes, and we have for number 17, and we have this function f of x. Okay, this is already going to be in simplified form. And here we have f of x, okay, we have is equal to 8 over x minus 4. And just for the restriction on the function, okay, so x minus 4 cannot be 0. Okay, so we have that x cannot be equal to 4. And we have for the domain, okay, so we have those values of x less than 4. Along with those values of x, okay, which will be greater than 4. Right. And in the case of, oops, wrong function. Okay, now 8 over x minus 4, okay, that function is already simplified, or already in simplest form. And since it is, okay, so we have x minus 4 remains, as opposed to canceling out completely. And because the factor remains, that means that the exclusion from the domain is going to be the vertical asymptote. Okay, so there is no denominator factor to completely go out, so there's not going to be a hole this time around. We have that exclusion, okay, to be converted to a vertical asymptote, and just providing, okay, the visual on this one. Okay, so you're going to have the graph of f of x, okay, to be split into two separate sections, and okay, and this time with x equal to 4, okay, again, because the denominator does not completely cancel, but instead remains, okay, this is going to be a vertical asymptote, and again, it's going to split the graph up into two sections. And let me mention this, okay, for vertical asymptotes, the graph of a function never touches a vertical asymptote. There are other types of asymptotes we will be looking into, and there might be some extenuating circumstances where they might come into contact with the graph of a function, but in case of a vertical asymptote, never. Okay, so vertical asymptotes, okay, those are always off limits. Okay. Now, for what we have in the case of, let's see, the next one we have number 18. Okay, so we got g of x and we have a constant over a binomial in this one. Okay, we have 2 over x plus 7. Okay. So you have for the restriction, again, x plus 7 cannot be 0. So you have the x cannot be negative 7. And for the domain, okay, so you have those values x less than negative 7. You have those values of x which will be greater than negative 7. And for 2 over x plus 7, okay, again you have this bit of history to repeat. Okay, so you have 2 over x plus 7. Okay, again you have already in simplest form. And so we have x plus 7 remains, as opposed to canceling out just like x minus 4 earlier. Again, because the factor in the denominator remains, okay, we'll have, this time we have our vertical asymptote. It's going to be x is equal to negative 7. Okay. So you have, in the case of g of x, okay, so g of x is equal to 2 over x plus 7. And we have separate regions here. And again, they are split up, okay, by the vertical asymptote, which we have at x is equal to negative 7. Okay. Now, for number 20, okay, now going from f of x to g of x, and now we have k of x. Another way of saying y. Okay, and we have this set equal to x plus 2 all over 3x squared plus 8x minus 3. Alright, again we have the restriction that the denominator cannot be 0 in value. Okay. And for this trinomial, now this one is factorable, and you can do the stuff like factoring by grouping and finding out what the binomials will be. I think what I'm going to do with this, and since the digits are low enough, and since we're going to have integer coefficients, I'll just go ahead and factor out and see what combination is going to fit. Okay, so we got 3x squared now, a given. You have factoring out to 3x and x. and I want the right combination of factors of -3 such that when you combine the outside and the inside products, you're going to end up on the plus side at 8x. So for this one, let's see, I think this is going to be x plus 3 and 3x minus 1. So again, just double checking. 3x times x is 3x squared. 3x times 3 is 9x. Take away 1x, so we got 8x. -1 times 3 is -3. Okay. So we got these individual factors, and neither binomial can be equal to 0. So for 3x minus 1, if this cannot be 0, or 3x cannot be at 1, so we're going to have an exclusion in the fraction 1/3. As for x plus 3, okay, that cannot be 0, and we have excluded along with 1/3, we're going to have -3. And so we're going to have not one but two exclusions from the domain. Okay, so going from -infinity to the smaller of the exclusions, but not including. So we have approaching -3, and we have bypassing -3. So have those values of x such that -3 is less than x is less than 1/3, and with 1/3 as the second and last exclusion. Okay, the rest of the domain will be those values of x greater than 1/3. And in terms of the asymptotes, let's see if we have any that are vertical. Okay, so we got our k of x, and expressing this ratio in factored form. Okay, so we got with the factors, okay, we have 3x minus 1, and we have times the quantity of x plus 3. Okay. And so there's no common factor, so this is already in simplified form. Okay, so 3x minus 1 and x plus 3 both remain. And so for what this is going to signify is that we're not going to have one but two vertical asymptotes. Again, since 3x minus 1 stays, okay, we have a vertical asymptote at x equal to 1/3. And also, since x plus 3 does not cancel out, we have a vertical asymptote at x is equal to -3. And just looking at how the function is going to appear. Okay, so we've got two vertical asymptotes, and in terms of the nature of what we have for k of x, okay, it's going to split not into two, but this time around we're going to have three sections. Okay, and you're going to have the partitions created by the vertical asymptotes. We have to the right we have x equal to 1/3, and to the left we have x equal to -3, and again we have both vertical asymptotes are going to be off limits, so there's not going to be any contact with the function k of x. And again, we're going to be looking into other types of asymptotes, and tell you what, in the meantime, looking for the domain and the asymptotes. Or in this case, vertical asymptotes. Now we'll say our rational function will be r of x, okay, is equal to, and we'll say we have x squared minus 25 all over x squared plus 7x plus 10. Okay, so let's see what we get for the domain as well as the vertical asymptotes, if any, of this particular rational function. Okay, for what we have in the case of the rational function, where we have x squared minus 25 all over x squared plus 7x plus 10. Okay, again, for the domain, again, the denominator cannot be 0 in value. And here we have with this trinomial, okay, so this is factorable. So we have x squared goes to x and x. And factors of 10 that will add up to 7. Okay, so you have a positive 5 and a positive 2. Okay, so if x plus 5 cannot be 0, okay, we have that x cannot be negative 5. If x plus 2 cannot be 0, we then have that x cannot be negative 2. So we have two exclusions from the domain. And for what we have in the interval notation, so you have those values of x less than negative 5, and followed by those values x between but not including negative 5 and 2, negative 2. And finally, we have those values x which will be greater than negative 2. And looking to see if we have any vertical asymptotes. Alright, so we have, once again, so we have x squared minus 25, and we come out to x plus 5 times x minus 5 and in the denominator again we have x plus 5 and x plus 2. And here we're going to have x plus 5 to cancel. And for the completely simplified form, okay, so will go out to x minus 5 all over x plus 2. Okay, so we got two exclusions from the domain. Okay. And we could have had up to potentially 2 vertical asymptotes. But again, x plus 5 cancels and goes out completely. So this is going to signal that x equals negative 5 is a whole. And for x plus 2 remains. And since that factor remains the corresponding 0, okay, that is going to be the lone vertical asymptote. So in terms of how the graph shows up, generally speaking, okay, so we have r of x, okay, and in a sense, okay, we have x equal to negative 2, so that is going to be the vertical asymptote, and we have a hole at negative 5, okay, so had it not been for the hole, okay, we'd have r of x and to split up into 2 sections, but with the hole, you kind of have like one continuous section here, and then you have like 2 sections in addition, those values x less than negative 5 and those values x greater than negative 5 and less than negative 2. So you got like 3 portions to what we have with r of x. Again, there could have been up to 2 vertical asymptotes, but with x plus 5 completely canceling out from the denominator, okay, again, that part is a hole in the graph, okay, and only x plus 2 remains. So translating out, we have x equals negative 2 as the only vertical asymptote. All right. Now, for other types of asymptotes, we're going to have in the mix, okay, what would be referred to as horizontal and slant asymptotes. And for what we have in terms of classifying the types, okay, this is going to be contingent upon how the degrees of the numerator and denominator of the rational function are going to relate. Okay, so for horizontal and slant asymptotes, see we have for a rational function, so we have r of x is equal to, and we use kind of like the theoretical notation, like what I did with the end behavior of the graph of a function, and what we looked at transitioning what we have between long division and synthetic division. So we have like the polynomial again, so you have a of n, x to the n, a of n minus 1, x to the n minus 1, and so forth, okay, going out all the way to a constant, and we have over, so we have b of m times x to the m, so we have be of m minus 1 times x to the m minus 1. And we have going out all the way to a constant, okay, represented by b naught. Okay. So for this rational function, okay, where n is equal to the degree of the numerator, and we have for m, okay, that's going to be the degree of the denominator. Okay, now there are going to be four possible scenarios that can arise. Okay, first of all, okay, in comparison between the degrees of the numerator and denominator, if the degree of the numerator, n, is less than the degree of the denominator, okay, so if n is less than m, then there's going to be a horizontal asymptote. Which you will have that y is equal to 0. Now for the next case, if we have going from less than m to where if we have that n is equal to m, okay, you're going to have another horizontal asymptote. Instead of being negligible, this is going to come down to taking the ratio of the highest degree terms, okay, which will come down to a constant. So we just have a of n over b of n. Now, so you got less than m, then you have equal to m. Now, if I have that n is greater than m by 1 degree, okay, instead of a horizontal asymptote, there's going to be a slant asymptote. Another term for that is going to be oblique asymptote. Okay, and the slant asymptote, okay, this will be expressed in terms of slope-intercept. And since I already have utilized the m and the b, we'll just use different letters. We'll say we have y is equal to alpha x plus beta, okay, like alpha being in reference to the slope. Okay, the reason I'm not using mx plus b is because I've already used those in a different capacity. Now, if we have that n is greater than m by more than 1 degree, okay, essentially what's going to happen here is that you're not going to have either asymptote type. So you have no horizontal asymptote, and no slant asymptote. Okay, so for rational functions, okay, with polynomials in the numerator and denominator, if it has along with vertical asymptotes, anything else, it's either going to be horizontal or slant, but it cannot be like both with a horizontal asymptote and a slant asymptote. It's going to be one or the other. And if the degree of the numerator is like 2 degrees or more than what's in the denominator, you're not going to have anything for the horizontal or slant asymptotes. And to kind of provide a visual, and let's say that if I were to determine the domain and the asymptotes of the following. Now we'll say we have in the first case okay, so we've got r of x is equal to 3x plus 1. And so we have over x plus 2 okay. And we're going to have this ratio already in simplest form. Okay, so for x plus 2, okay, that cannot be 0. We have that x cannot be negative 2. So we have for the domain, okay, negative 2 is left out, so what will belong will be those values less than negative 2 along with those values of x that will be greater than negative 2. And for r of x equal to 3x plus 1 over x plus 2. Okay, again, ratio is already simplified. So we have x plus 2, the denominator. Okay, that is going to remain. Like it's not going to cancel out. So this means that the exclusion from the domain, that's going to be a vertical asymptote. And in terms of any other type of asymptote there might be, okay, so this will come down to the degree comparison. Okay, so we have with the numerator we have 3x plus 1, and the higher degree term we have at 3x, and this x is a first degree, so n is equal to 1, and in the denominator we have x plus 2, and the higher order term in the variable is just x, and this is also a first degree. So you have that n is equal to 1 and m is equal to 1, so you got the same values. So we have that m and n are the same. So you have n is equal to m, so you're going to have the second case out of these 4 possibilities to apply. So that means that there is going to be a horizontal asymptote formed by taking the ratio of the highest degree terms in the numerator and denominator. So you have a horizontal asymptote, and y is going to be equal to the constant resulting from taking the ratio of 3x to x. So this is going to be at y is equal to 3. So you got 2 asymptotes, vertical at x equal to negative 2 and horizontal with y is equal to 3. And this will be the essence of what we have here. Okay, so you got x equal to -2, y is equal to 3, and again we have again the vertical asymptote is off limits, and we have with the horizontal asymptote, okay, to the extreme left you're going to have this section of r of x to run tangent, and likewise to the extreme right you will have r of x to run below and tangent with respect to the horizontal asymptote, y is equal to 3. Now, another case here, let's say that we have r of x, and we have is equal to 3 over x plus 4. Again, the ratio is already a simplified form. So you have x plus 4 cannot be 0. We have x cannot be -4. And so we have for the domain, we have those values of x less than -4, along with those values of x which will be greater than -4. And okay, and again, 3 over x plus 4, again we have in simplest terms already. So x plus 4 is not going to cancel. And the excluded value from the domain, okay, that's going to lead up to the formation of the vertical asymptote. Now, where the degree comparisons come in, okay, if you notice, okay, we have for 3, okay, we have we're going to have the n is equal to 0. And why is that? That's because we don't even have a first order or any kind of x term. So anytime we have just a constant, okay, the degree is going to be at 0. And for what we have with x plus 4, the higher order term is x, and this will be a first degree. And in terms of what we have in the relation between the values of n and m, okay, we have the numerator degree is less than that of the denominator. Okay, so we have the n is less than m, so we have a horizontal asymptote, y is equal to 0. Okay, so again we have a couple of asymptotes, one vertical, one horizontal. And in terms of the general behavior of the graph of this particular rational function, okay, so we got the vertical asymptote x equal to -4. Okay, And the horizontal asymptote, we have y is equal to 0, so that is going to be the x-axis. And for what we have in terms of the behavior of r of x is equal to 3 over x plus 4, okay, we have that behavior indicated by the curves in the upper right and lower left sections. All right, now another special case here, and this is going to be kind of in close proximity to what we looked at earlier this week. And for rational function we have here, we're going to have the r of x, okay, is equal to x cubed plus 5x squared plus 3x plus 1 and this is going to be all over x squared plus 1. Okay. And this is going to be a special case here. Now, again, looking for the domain. Okay, again, we have a rational function, and we cannot have a zero-valued denominator. Okay, so in this case, x squared plus 1 cannot be 0. Okay, now in the real number system, I can take a difference of squares and factor into integer coefficients, but I cannot in the case of the sum of squares, x squared plus 1 being a case. And what I can do is I can separate the x squared and the 1 and just have it set it whereupon when I have x squared cannot be negative 1, and follow through along the lines of the square root property. Okay. And where I have instead of square root property of equality, and we'll have it like square root property of, in this case, non-equality. Okay, so we have for x squared, so if we go from x squared to x, we have the x cannot be plus or minus the square root of negative 1 so the x cannot be plus or minus I. Okay. So in terms of the domain, what is this going to mean? Okay, well, the excluded values are not even in the real number system, and we have, again, we left behind, okay, the complex numbers. Okay, so you have only complex roots are excluded. Okay, so no real values are excluded. Okay, and so we're going to have some consequences from this. It says no real values are excluded. That means I'm not excluding 0 or any positive value or any negative value. So in the case of the domain, we're going to end up with a set of all real numbers. Okay, so the interval notation, you have parentheses around negative and positive infinity. And since there are no real values that are excluded, that means there's no exclusion that's going to be a whole or vertical asymptote. So for any vertical asymptote, okay, that one does not exist. No whole exists, and no vertical asymptote exists either. Okay. Now, with no whole, no vertical asymptote, okay, that is not to say that we don't have any type of asymptote. and looking at what we have for the degrees in the numerator and denominator. Okay, so we have in the numerator, okay, so we got x to the third. So we have the n is equal to 3, and in the denominator we have the higher order term at x squared. So we got n is equal to 3, and m is equal to 2, and 3 is greater than 2, and we're going to have, in the scenario, we're going to have the n is greater than m by 1 degree, and we're going to have a slant asymptote. Okay, now we're going to have a straight line. Okay, so while we don't have a vertical asymptote, we are going to have a slant asymptote. And in terms of how we're going to arrive at this, okay, we'll be looking at polynomial division. Okay, and so we have in the setup, okay, now we got x squared plus 1, and I'll do, just for zero placeholder purposes, we have the 0x. Now, it's not so mandatory for the divisor as it is in the case of the dividend. Okay, so you got x squared plus 1 into x cubed plus 5x squared plus 3x plus 1. Okay, and if I could, I would perform synthetic division directly, but since I do not have a first order binomial expression, it's with that second degree that, okay, line division is called for. Okay, so looking at the leading terms, if I take x squared into x cubed, okay, so going x times, and we have distributing, okay, so we have x cubed, we got x times 0, it's got 0x squared, again this is for placeholder purposes, and it got plus x. Again, with line division, I'm looking at row by row subtracting. So I got x cubed minus x cubed, and we have 5x squared minus 0. Okay, so this will be 5x squared. And we got 3x minus x. So this will be 2x, and I can bring down the 1. Okay, so to x squared and x cubed, again going x times. Now, I can now take x squared into the leading term that is spun off from the first round of line division. So x squared into 5x squared, this will go 5 times. And distributing, so we got 5x squared plus 0x plus 5. And we have subtract, so 5x squared goes out, and we got 2x minus 0 is 2x, and 1 minus 5 is going to be negative 4. And I cannot take x squared directly into 2x since the divisor now has a degree in the leading term that's too great for what we have left over with 2x. And for the slant asymptote, okay, I'm not concerned about the remainder. I'm just going to be looking at what is in the quotient. So for what we have now, okay, we got the quotient at x plus 5. So there is going to be one asymptote. and this is going to be at y is equal to x plus 5. And just looking at how this graph is going to appear, and for a lot of these slant asymptotes, in terms of drawing it and seeing how they line up with the graph of the function, trying to do it by hand, it can be about like pulling teeth. Okay. And for what we have in the layout that we have, and I'm going to zoom in. Okay. So for this wave, okay, that we have in red, okay, that is in correspondence to the rational function x cubed plus 5x squared plus 3x plus 1 over x squared plus 1, and I got the slant asymptote. So you're not looking at totally horizontal or vertical. Okay, so you have just kind of a sideways or oblique pattern. And if you notice, you have the extreme ends, extreme left and extreme right. Okay, you have the curve of r of x, okay, to kind of have almost like a parallel line formation. But if you notice, again, I said that vertical asymptotes are off limits, but for the other types, like horizontal and slant asymptotes, under certain extenuating circumstances, you might have a bit of contact, whether it is touching or crossing. And notice, reading from left to right, okay, now we have the slant asymptote above the graph of r of x, and once we get around, okay, the origin and go past, notice you have going past, it looks like x equals 2, that you have a bit of a turning point, so to speak, where you now have the wave representing r of x to now be situated above the slant asymptote. So there can be contact, even intersection between the function and the horizontal or slant asymptote under extenuating circumstances. But again, with vertical asymptotes are absolutely off limits.